you'll be in the background because hello Zoom. You'll be in the background because we have this little iPad up, and the only real purpose of the iPad is to see so that anybody who is at home can see their classmates, because sometimes we have our classmates answer questions. So it's important that they be able to know what's going on. So
I have LED lights like surrounding my room.
These kind, they're fun, right?
Yeah.
I enjoy them.
Where's the little remote thing?
It's actually stuck on the back wall, so I can change them if I want to.
And usually, is there like a fade thing on there?
Probably. I tried to keep them non-distracting, you know.
It's like a fade thing on mine.
Mm-hmm.
There's like a fade 7 and a fade 3.
Oh, okay.
That means the colors that it changes.
Got it.
And it like fades to different colors.
That makes sense.
Yeah.
So now this is on.
I like fade 3.
Fade 3. What does fade 3 look like?
It's like changes from blue, red, and green, I think.
Well, that's cool. Hello.
Hello.
Cool.
McGinnis Ferry's basically closed.
What is McGinnis Ferry? Oh no, that isn't great. Why? Oh, okay. That's
I went to
crazy.
At Town Center because that was closer.
Dude, you have to bring me smoothies if you do that. Like, that'll be part of the thing. You know how much I love a smoothie. Cole, did you meet Cal the other day? You don't even hear me. Hey, Cole.
Yeah.
When you were here the other day, did you meet Cal? This is Cal in here. Okay. You're allowed to do that. We'll let you do that. All right. See, there you are right there in the corner. And then that way, anybody who's going to watch it at home, and there isn't anybody today that I know of who plans to watch at home, but sometimes what'll happen is you'll be in class here and then you'll have a question. You're like, what did she say about this or that? Right. And you can go back and look at it because it'll be on the YouTube channel every week. So you can always go back and watch the lesson and go, oh, okay, I missed that part. Sometimes your brain goes, you know, and then you forget what happened. So that's what that's for. Or if you're going to be absent, you can also watch it like, you don't have to watch live, it's recorded, so you can watch it later. So at any time you can come back and watch it, which is really handy.
I'm pretty good at like muscle memory and stuff.
Oh, are you? Do you do a sport then?
I don't do a sport, but I do like games.
Oh, video games? What do you do? What's your favorite?
Maybe Warzone or Roblox.
Oh, Roblox. Okay, yeah, my boys have played Roblox. I don't know much about Warzone, but I know my boys have done Roblox before.
It's a shooting game.
Uh-huh.
It's really, well, it's like.
Is it like Call of Duty or any of those? Or
Yeah,
they play Call of Duty.
Do you know what Fortnite is?
Mm-hmm. Yeah, I know Fortnite.
Fortnite copied them.
Okay, yeah.
And a lot of Fortnite players have switched to Warzone.
Really? That's pretty cool. They both played Fortnite when it came out. Cole played it a little, Drew played it a lot. And then they
I used to play it for like 3 years.
Okay, that's pretty good. That's pretty good. I had a Nintendo 64 when it came out back in like 1989 or whatever. And I would play the original Mario Brothers sometimes and like Duck Hunt. And there's a game, it's still out and they've, updated it and made it work on the new systems, but it's called Castlevania. I don't know if you've ever heard of that,
No.
but basically it's this big castle and it makes me crazy. Your goal is to get to Dracula at the end and kill him. And so there's a guy that used to hang out at the house all the time, practically lived there, and older teenage guy. And he loved that game and he played it and played it and played it and played it. And then he finally got, because the way it would work is you're in a level and if you don't beat the level, you start like over at the beginning of the level.
Yeah.
So you have to keep building, right? So he finally got to Dracula and he was ready to fight Dracula and he had like an arsenal full of stuff that he'd earned. He was ready to go, right? He was ready to go. And he took a break to like go to the bathroom, get something to eat, prepare mentally for this challenge, right?
And then it restarted him.
No, he mouthed off to my best friend and she went over and unplugged it. She was mad. So she went over and she was like, and just pulled the plug out. And we had you know, those chest freezers, the kind that it's like a box, you keep them in the garage usually, and you lift up the top to put meat and stuff in. And he picked her up and put her in our chest freezer. He was so mad at her. It's one of those memories I'll never forget because it was crazy. Like, why does that happen?
I met this guy on Fortnite when I first started playing.
Yeah.
He said a lot of curse words, but he still does.
Yeah.
And he's 9. That's the surprising.
Oh
part.
my goodness. Wow.
His cousin does too.
That's crazy.
They're both 9. And oh, okay. So
Does he live nearby or is he?
no, he lives in Washington.
Oh, state, Washington State?
Mhm.
Oh, wow. So the actual other side of the country. That's pretty cool. That's a long ways away.
And I met someone on my VR from Iceland.
Oh, really?
Yeah.
Wow.
I don't really play my VR that much anymore though.
I would love to go to Iceland. That's on my list because I'd like to see the Northern Lights and all those. I know there's places you can walk at parks that are full of big, just ice cliff walls. and
Oh.
It sounds really pretty.
Yeah.
I'd like to go there. That's on our list. We're going, like, in October, we're taking that little break and we're going on vacation to Nova Scotia, which is in Canada. It's like an island on the far eastern side of Canada. And it's really long. And hush. It's where my grandfather is from. He was born and raised there. And so growing up, my mom went a lot. And I went, I think 3 or 4 times as a kid, but I haven't been since I was like 15. And my boys have never been, and my husband's never been, which is crazy because he travels all the time. So the fact that he hasn't been to Nova Scotia is kooky. Here's your other partner in crime. So yeah, it's a little exciting because they've never been. Hey, come on in. How are we doing? We're good. All right. So like I was telling you guys when we had our meeting, Darcy and Lewis are probably going to join us at some point. And they're super fun. You'll like them both. Just for now, but they'll come. And you know what? Something about this class, I tend to add 1 or 2 people like mid-September, because there's usually somebody scrambling who's like, oh, I forgot to do something for science. But the other class is huge because I had, I think, 4 of the kids that were in this class last year move up, which is part of the reason this class is smaller because it used to be built out of those kids. So it's kind of like a rebuilding year, but that means you guys will have a lot of fun because we can spend more time on stuff. But when Darcy and Lewis come, they're at, what are they at? Veritas, I think, which is like a hybrid. Yeah. You didn't like it? No. Well, they're there now and their mom's just not sure how much time their work is gonna take. So they're gonna do some time there before they decide whether they're coming back here like full time or whatever.
I toured Veritas and LCA, and LCA was actually really good.
Which one's LCA?
The New Christian Academy.
Oh no, wait, they're not Veritas, they're Ardios. That's right.
Oh my gosh, it's even worse.
You didn't like Ardios either?
No, I went to Audios. Like I could tell you all the inside stuff if you wanted to know.
That's funny. Well,
One is
I never did either with my kids, so I don't know.
90% based off of favoritism.
Oh, that's not fun. That's no good.
Yeah, because I was going for like a role in the theater, and they gave it to the kid who's been going there for a while. And they gave it the other role to the kid who's going there for a while.
Oh my, yeah. Well, sometimes in theater, that stuff's kind of earned by seniority. They tend to do that. Like, oh, it's his
And then with
turn.
class, I'd raise my hand. They'd only ask the kid.
Oh,
And
why
plus
would you do that?
The kid who's been there for a while was awesome. He was also in the theater. His mom was a teacher,
Mm-hmm.
and he never failed a class.
Oh, man.
He never got below an A+, which I doubt
Ah.
the kid was.
Yeah, that's the world for you, Mitchell. So, all right, Mitchell and Cal, let's get going. Let's see what we can. So we're going to take there's gonna be a little time at the beginning where we're going to review some of the how to science stuff because that was in your pre-lesson, right? And then it's also in your lesson, some of it was. I might sit over here because I have a clicker now. I don't need to be over there. I think we'll go. It may not go on this first slide because of the way it's situated. Let me get the first one.
I never liked.
No, I liked some things about school. Okay, so here we go.
I like the creative
I
writing.
liked it when I was in kindergarten, but I
Mhm.
because I actually got to speak,
Yeah.
but I hated it. I hate it now.
Oh, yeah. Well, hopefully this will be different. Hopefully you'll like this
I
school because this
also-
is fun.
I also hate home.
Oh, well, hopefully this will be something you look forward to every
It's
week.
better than normal school though.
Yeah. You gonna go your week? Come on, you're supposed to be
Like-
awake.
2 hours. And
No, it's not gonna go. What's it doing? Make sure
You're not
it
doing
goes.
stuff. Takes you like 5 hours.
5 hours?
I'm taking high
Used to
school
take-
credits.
I used to take me 7 hours.
All right, now it's working. It had to wake up for a minute.
I'm doing, I think I'm doing 11th grade health,
All right,
no, geography, and I'm doing high school health as well.
all right.
Extracurriculars.
So let's talk about what science is. You guys should know some of these by the blanks. Now, here's something I do that I didn't bring up in our grill and chill. So I have a little jar of coins. Now, you may have noticed that I have like an old antique bubblegum machine by the front door. It has M&Ms in it right now. They're still like I put a whole bunch of those springtime M&Ms, so they're like pastel color ones.
It's a gumball machine.
It's a gumball machine, but it has M&Ms in it at the moment.
I would love some.
So the way that this works is if you answer a question, I will put a coin in a pile for you. And then on your way out, you can put the coins in the machine. It takes all coins. So it doesn't matter if you get quarters or pennies, it's all the same. And it usually spits out between 2 and 3 M&Ms each crank. So what I do is I'll let you answer questions. And if you've gotten 3 right, then we'll wait till your other classmates get up to the point where they're getting close to 3, and then it can come back to you and you can keep adding. That make sense?
Thanks.
Cool. All right. So,
I don't really like M&Ms.
well, I usually change it. At some point we'll have Skittles or jelly beans. It changes.
Don't put Skittles.
No, don't like them?
No, there's actually, they're the worst thing. No, like, they have iron in them, like, they
Oh,
have titanium,
vitamins. All right. Well,
they're actual metal.
yeah, titanium actually isn't really a bad thing if you eat it like in small amounts. It really actually doesn't hurt you. I do cake. I do. Well, you need copper, you need iron, you need a lot of vitamins that are minerals. They're actual minerals that are like selenium, things like that, that are metals and whatnot. You need them for
You know
your
that-
regular
like
functions within
the-
your body.
In like the 30s, there was like a drink that was made with uranium, like it
Well,
was.
that's surprising. There were a bunch of women who painted watch faces with radium because they glue in the dark. And the radium is cancer causing, right? It's carcinogenic. And they were told to like lick the brush, like, so it was really pointy and their jaws rotted. It was fun. So science is a system of knowledge and a method you use to find knowledge. So this is the way your textbook put it. Science often begins with something and ends with something. Does anybody want to take a guess at what it might be? I think you've got a biology book.
Life science.
Yeah, that's a life science book.
I know, I told my mom I don't need it.
Yeah, you need an earth science book.
That's what I said.
Yeah, that one won't help you. So I'll help you out. So this is going to be science often begins with, it says it's not gonna, do you think? Well, I clicked the wrong button. Oh, come on. It doesn't want to work today. It went back. So it should go this
Wanna
way.
know something about
Clicker,
my
clicker,
funny?
clicker, clicker, clicker. I'm going to use my thing. So science often begins with, it'll go curiosity, and then it ends with discovery. You could say questions and maybe answers. Sometimes they're not always answers though, because sometimes though you have discovered something, it's just going to lead to more questions. So what is the use of knowledge to solve practical problems? Do you know what that might be? If you came up with an idea, a way to solve a practical problem. So that is what we call technology. And technology, you probably think of technology as like iPads and cell phones and computers and things like that. But a pencil is technology. A shoelace is technology. All of that is technology.
Back in the day, it was new things.
Right, they were new things, and you've taken your knowledge, what you know about the world and how things interact, and applied that knowledge to solve a problem. So even like sunglasses, well, the problem is it's really bright outside. So what do I know? I know it's bright because the sun is putting a lot of light into my eyes. So what do I know that might, reduce that light? Let's look for some sort of translucent material that we can use. And then how do we keep it on our eyes? Well, we'll use our ears because I know my ears are here and regular glasses work there. So that kind of stuff is technology as well. So you're early. You don't have to be here till 10:45, You're just hanging out? All right. So here's where we talk about our branches of science. So we've got formal sciences, natural sciences, and then one other kind. Do you know what kind that is? So that's what we
Web
call,
science,
what kind?
web science. Yes.
Whoa, so it's actually going to be, that's what we call our social sciences. Okay, whoop, go on, click thing. So those are
Besides
social
geography.
sciences. Yeah, so these are things, geography doesn't just study landforms, we do study landforms, but also in geography, you study kind of how the cultures are dispersed throughout the earth. So these are social sciences because they deal predominantly with people. Anthropology is the study of how people used to live. And if you hear about like forensic anthropology, that's usually people who study bones and skeletons. And these are people that work with everything from like mummies to crime scenes. So they do a lot of stuff. So in physical, so our natural sciences are life science, which is what we did last year in this class, that's biology. And then we have different kinds of physical science. So this one here is the study of nature and the properties of matter and energy. And that's what we term as physics or physical science. There's a difference between like a physics class and a physical science class. We do physical science next year. Physics class is much more high level, lots of math, lots of equations. We do physical science, which is sort of like the intro you need before you do a physics class. So we have something that's the study of celestial objects, space, and the physical universe. Does anybody know what celestial means? Know what celestial means?
Is that astrology on your thing?
Yeah, that is. Oh, you got one. Okay, so look, it's astronomy. You're close. So astrology, those are the people that work with your zodiac sign, and they say, oh, you're a Leo, or you're like, I'm a Pisces.
Zodiac sign is basically racism for girls.
Oh. I think you two are going to get along. I think you two are going to get along really well. So yeah, so
Great.
that's astrology. Astronomy is studying the stars. That celestial means heavenly bodies or things in the sky. So I'll give you a tip. When you get to college, if you're like not looking at having a science class, and like you're not going to major in science, a lot of people will say, oh, I'll take astronomy. That's easy. I just have to memorize some constellations. A lot of people get duped like that. That's not an easy class. That's actually a really challenging class in most colleges. So yeah, and we had a friend who in high school, he wanted to sign up for astronomy. No, he wanted to sign up for cosmetology, and he signed up for cosmopology, and he signed up for cosmetology. So he thought he was studying planets, and instead he was learning beauty, and it was hilarious. So what do we call the study and identification of substances of which matter is composed? Think about that one. Matter is anything that has mass and takes up space. So it's basically all the stuff in the universe. So we talk about what it's composed of, that's chemistry. And that's a really fun class. We'll do that in 2 years. And then lastly, this is what we're doing this year. This is earth science. So it's the study of the earth and its atmosphere. So when you see this, remember, this is something you're going to want to memorize. That's your engrave it on your brain, engrave it for eternity, because it's something that'll come back again, probably on some exams. Remember that. Okay, so we have some big ideas in physical science. We've actually got 2 pages of these. So what do you think this one might represent?
Space and time.
That is space and time. That's great. Okay. And we're looking at physical science because earth science is a physical science, right? And then what do you think? I think this one was, oh, I can't remember which one was next. Anybody want to guess what any of the other 3 are? What this might be? This one's I gave you a clue with the symbols. And this one. So
Something Navy related.
yeah, not quite. So this is energy.
Which is
All right.
forces in motion.
Yeah, forces in motion. I clicked wrong.
Yes.
There it goes. So yeah, forces in motion, right? Forces. I gave you, all of our arm. These are all of our armed forces, right? What's this one? You know,
Very hard.
Marine,
That one's
Air Force. What's that one?
Coast Guard.
Yep, that's Coast Guard. That's Navy, Army, and what's this one then? What's the new one?
I haven't seen that one.
That's Space Force.
That's a thing.
Yeah, that's a real thing. So this right here, this is going to represent matter and change. Okay, this little symbol looks like a triangle. It's called delta, and it's a Greek letter, and we use delta in science to represent change very often. Sometimes you'll even hear people say it like, what was the delta of your equation? And they're just meaning like, what's the difference? What was the change? But delta, you'll also see like when we get to studying like the way rivers pour into oceans, they tend to widen and make this shape. And they call that area the delta because it's a triangular shape. So you'll see a lot with that symbol eventually. So how would you define space? Anybody want to give it a shot? What do you think space is? It's a hard one to define.
I don't want to be wrong.
Yeah, well, it's hard to define. So it's this continuous area or expanse in which free, available, unoccupied, this kind of thing, right? It's a very abstract concept. And the dimensions of height, depth, and width, that makes sense, right? Width, depth, height, that has space. And all matter exists and moves in space. So that's something else to think about. Like you think about this room and you go, oh, there's all this space right here. But what's in that space? There's space, but what's in it? Is there nothing there? There's matter. What kind of matter is right here? All around you. There's gases, right? There's air. There is oxygen, but there's predominantly nitrogen before oxygen. There's more nitrogen in free air than oxygen. But yeah, so you want to say that it's empty. Like you could open a door to a room that had nothing in it and go, this room is empty, but it's not empty. It's full of matter. And you have to constantly remember that, because the way you think kind of in everyday life isn't the way you think about things in science. So time is a difficult one. So time is measured or measurable period during which an action, process, or condition exists or continues. And this is a fun one, a non-spatial continuum that's measured in terms of events which succeed one another. So an event after an event after an event. And the period in which the events take place, be that, night turns to morning or I snap my finger, that's all time. So forces you would define by saying, this one's easier. A force is a push or a pull on an object. That's pretty much what force is. It's a simple one. A force is a push or a pull on an object. And then it usually results in some kind of interaction with something else. So motion is a change with time of the position of a body. So it doesn't mean a person has a body. It could be a ball. Okay, if I move the ball, if I roll the ball across the floor, it changed position during the time in which it was rolling. That's motion, okay? And this will be more of a thing when we get to physical science, but this will come up when we start getting to like space later on. So matter, it's in the way, is this observable substance. Energy is based in matter, but the easy definition for matter is it's anything that has mass and takes up space. And that's going to be one there that when we get back to matter again, we'll come up on it again. When we get to that again, that's going to be one of those engraved on your brain. Matter is anything that has mass and takes up space. So is there matter in the quarter?
Yeah.
Yeah. Is there matter in the air all around you? Yeah, unless you're in a vacuum, you've got matter. Okay. So change, how we define change. So that's a transition. It says from one accepted theory to another, or from one process to another, or an alteration of a substance. Any of those things can be change. That's definitely a difficult one to define. Energy, though, is a little easier. So energy is the capacity to do work. You have to then define work if you really want to get into it. And so work is a whole other definition that when we get to physical science, we really pay attention to. But energy is the capacity to do work. And that's why a battery is really good. Because if you put a good thing to remember, if you put a battery on that table, is it going to do work? Like, is it going to make say you had one of those toys that you pop battery in and those little guys that walk across the table, them, they spit sparks or whatever. Yeah.
What?
These little dudes, they're little dinosaurs, they walk and they spit. Well, it could be anything. It could be a remote control car. Oh, they're cool. Now, if you had one of those toys and you put the battery on the table, it's not doing any work, but it has the capacity to do work, meaning it has the ability to do work. You just have to plug it in.
I think if you put two batteries between a glass of water,
Mhm.
you can make it funnel because of it.
Sometimes, yeah, if you've got everything lined up correctly. Actually, I have a video on my channel that you can look at where we made a little wire loop, and we used some batteries and we made the wire loop spin. It was standing on two little posts and it spins and spins, and it's a lot of fun. It's easy to build.
You can put like a battery between like a copper
Mhm.
spiral thing.
Yep, we'll be doing lots of those kinds of things next year in physical science. So earth science in particular, what are our big ideas? Our big ideas are systems. So a system, Earth is a system of systems. So you've got a universe, and within the universe, you have solar systems, right? And then within the solar systems, you have your planets. And then within your planets, you've got all kinds of systems. Like we have an atmosphere, a biosphere, a geosphere. We have a carbon cycle. We have all kinds of things going on. So we have systems, you have systems inside your body. And so systems, and if you ever go into engineering, systems are going to be like your life, because that's what engineers do. Systems. So Earth is a system within systems, and it has systems inside of it. So we think about systems when we think about Earth science.
I wish I was kind of systems.
Yeah. And then energy. So the flow of energy drives the cycling of matter. So matter cycles here on Earth. So right now, I have a quarter here, and well, a better example would be a nickel. Nickel is an element, and a nickel contains actual nickel. So was it always in a coin? No, it was once a rock, right? But if that nickel gets the nickel I'm spending gets really, really damaged, and it makes its way back to the US Mint, they're gonna melt it down and stamp out another nickel. So that nickel just cycled from being, an element within the Earth. It could be mined like a rock, and then it got melted and made into a coin, and then it got melted again and made into another coin. And then you've got like these trees out here. Okay, so they drop their leaves on the ground. Those nutrients get down into the soil. Eventually, they turn to dirt. The tree uses its roots to get nutrients from the dirt that go back up in the tree. So it's all a cycle. And it's all about energy in those cases. So life in the environment, life including human life, influences and is influenced by the environment. What's a way that we as humans influence our environment? You can think of something, Cal. What's the way that people influence the environment?
I don't understand a lot of words.
Okay, so the environment means like the place in which you live. Forsyth County is an example, okay? So what's something that people do to influence or change or impact the environment? Yeah, everything, true. Can you think of like a big thing we do? You know what happens in this county all the time? People are building and building and building. And in order to build, what do they have to do first with a piece of land, They go in with all those, they go in and they tear down all the trees, right? And knock it all down and they level it out. That's the way humans impact the environment. So the way the environment might impact us, well, the environment's everything. It includes this whole area in which we live. Rain and stuff is part of the weather that impacts the environment. And that can certainly impact us, because what if it doesn't rain enough and we don't get enough crops? Those things growing in the ground, that's our environment. Those are part of our environment. If we don't have them to eat, what's going to happen to us?
You die.
We starve and die. Yeah. So humans are part of that. And the same with every other living thing. So this is interesting. The unchanging drives change. So physical and chemical principles don't change. Those are typically laws, scientific laws. A lot of them don't change. And though they don't change, that drives the change in everything else. So the fact that, what happens if you mix water and baking soda together? Have you ever done it? I'm sorry, vinegar and baking soda together. What happens? Do you know? It fizzes, right? It blows up, makes bubbles, okay, and it fizzes. And we know that's going to happen because vinegar is an acid, baking soda is sodium bicarbonate. So you have acetic acid, sodium bicarbonate, you mix them together, and an acid-base reaction always produces a gas, a salt, and a water. That is unchanging. But when you mix them together, you create a gas. So now you've changed that part of the environment around you. You've added something that wasn't there before because you changed the chemical composition of those things that you mix together. So because those principles are unchanging, they drive change. So modeling and mapping, we're going to do a lot of modeling and mapping in this class. All right, so science is awesome. Science and your perspective. These are things to remember as we move through science. So it's a process and a body of knowledge. So you can say, I've learned a lot about science. You could be talking about either the process or the knowledge. And this is something to remember too, especially now. So we're going to talk a lot about how in this class, just kind of how the media present science, how society in general understands science. Can you think back to like a year or two ago when there was all this argument about whether or not you should wear masks because of COVID and whether it was good or bad? There were people arguing it. Do you remember, like at the very beginning, really arguing it?
Why are you going into politics?
No, it's not politics. That is part of the scientific process, is going through those changes. And the CDC, who's our kind of like our, advising body when it comes to science and how it interacts with society, they would say one week, they would say one thing, well, we think this, and then the next week they say something else, and people would get mad and they go, they don't know what they're talking about. They keep changing their minds. Why are we listening to them? Well, actually, they're doing science because science changes. That's the process. You get new information, You make new decisions based on that information. So although it confused people and frustrated people, it's actually the process. People just aren't used to that because they aren't educated well in the fact that that's the process. And you have to kind of keep on top of it. So be skeptical. What's skeptical mean? You know what that means? You know? So skeptical means that you question things. You don't take everything at face value. If I told you the sky is purple today, you don't just believe me because I said it. You go and figure it out for yourself, or you research it if you can't go figure it out. Maybe you can't figure it out. You can't get outside. You're locked in a padded room, and you need to be able to get that information somehow. So this means always verify yourself. Don't just take people at their word, and ask questions. Always ask questions. If you have any question about anything, well, why did that work? Ask, because that's how you learn, right? And then you have to believe in the process. So this doesn't mean like throw away all of your this doesn't mean like just throw away all of your skepticism that we told you to have just a minute ago. It means that the process of science, where you have a hypothesis and then you run an experiment and you keep your variables the way they're supposed to be, very limited, then you can trust that the process is right because you're doing it right. So let's see, using a scientific approach. We're going to breeze through some of these quickly because I'm watching our time. So whoops, I clicked that earlier. So scientific method, this is your organized plan on how you're going to go about discovering and then communicating what you've learned, okay? And the goal of scientific method is to solve a problem or better understand an observed event. All right, so here's the thing about doing science with scientific method. You have to use scientific method, otherwise you're not really doing science, you're just playing. So here's the difference. Say, Cal, say every day you tend to get headaches when you're at a friend's house in the afternoon. You go there every day for whatever, your mom has hair appointments and you go to
get car sick no matter what.
okay, there you go. So say, okay, that's a good one. So you get car sick. All right. We'll use that as an example because I do too, really bad. Are you better in the front seat? I'm way better in the front seat. The back seat, I can't, man, is rough. So you get motion sickness. All right.
The age that you're supposed to be when you ride in the front seat is 13.
Yeah. So, but some people only have like a truck, so they don't have a choice, you know. So if you get car sick, all right, so say you hypothesize that the reason you get car sick, what color is the interior of your mom's car?
Black.
Black. Okay. Let's say that you hypothesize that the reason you get sick in the car is because the color black makes you sick. How could you determine whether or not that's true? What could you do? Does your dad have a car?
Yeah.
What color is his inside?
Black.
Okay. Anybody else you know have a car?
Um,
Grandparents, uncles? Okay. What color are their cars?
my grandma's car.
Everyone is black. Have you ever been in a car? Have you ever been in a car that's okay? My van has some black, but a lot of tan. Okay. So if you think that it's black that's making you sick, the color black makes you sick, could you try riding in my tan van and see if you still get sick? Yeah. Okay. So what variable did we change? We changed the color that you're seeing. Now, if you still get sick in my van after repeated trips, what did you learn?
It's not that.
It's not black that makes you sick. You're still sick. So then you come up with something else. Okay. I get sick in the car because the air conditioning is blowing.
It never blows.
Oh, okay.
The back one doesn't.
It doesn't blow. Okay, so I get sick in the car because the air conditioning doesn't blow. How could you determine whether that's the cause?
Make it blow.
Make it blow. All right, and you still get sick. So now what? So these are all variables. These are things you try. So why do you think you get sick in the car? What's your hypothesis? You know?
I don't know.
You don't know? Okay, so most people that get motion sick in a car, it has to do with your vestibular apparatus, which is in your inner ear. And it's basically a lot of spirally looking tunnels and stuff like that. And they have fluid in them. And that fluid tells your brain whether or not your eyes are looking at the horizon, right? Like this. So if you tip your head, it tells your brain, oh, my head tipped, not the horizon, right? But everything around me didn't move, I moved, right? And with people that get motion sick, something in there doesn't communicate accurately. So something in your vestibular apparatus and your brain isn't communicating accurately, and it gives your brain this impression that you're like doing all this crazy business, and that makes you sick. So things you could do to determine whether or not it's your brain and your vestibular apparatus making you sick is ride on all kinds of rides, do all other kinds of motion. If all of it makes you sick, then it's probably motion, right? Not color, not air conditioning.
I don't get sick on roller coasters.
There you go. I don't the first or second trip. And everybody told me it would get better when I got older, but it got worse. So I hope it gets better for you.
Do you know those like shark? It's like a ice ride or
Mhm.
something.
Yeah, I think I know what you mean. Yeah.
I went to the fair and I rode on that
Oh,
the
yeah.
first time,
Mm-hmm.
and I didn't get motion.
Yeah, the faster rides make me less sick than the slow ones, like boats. Ugh. So that's scientific method. You have to limit your variables, right? So what do we call information that we get through our senses? What are your senses? Taste?
Taste, touch.
Yep.
Smell.
Mm-hmm. Taste, touch, smell. There's two more that we usually
Sight.
think of: sight, and
Listen, I don't know
hearing.
what that is.
But there's actually one other that we don't usually think: taste, touch, sight, smell, hearing. Your five senses. Really, you have more than five, huh? Oh no, you're thinking of states of matter.
Oh,
Mhm. But there's a sixth one that's really important that we don't think about much. And that one, whoop, the word just went whip. I love it. Lupus is fun. It's called Drew, what is it? Help me. Proprioception. Thank you. It was a P, it wouldn't come out of my mouth. Proprioception. That is, where is your body in space? And that does deal with your vestibular apparatus. But are you sitting? Are you standing? Are you standing on your head? Are you riding in a car? Are you tipped sideways? Your body knows where it is in space, right? This is why pilots have very great proprioception. They know where they are in reference to the planet, for example, the surface of the planet. Gymnasts, both my boys are gymnasts. They have great proprioception because they can turn their body in the air and know how they're going to land. Divers do the same thing. So all that is really important. So we call things we gather through our senses observation. So you mix vinegar and baking soda together and it bubbles. You observed it. You saw it with your eyes. You heard it. You probably smelled it. That's an observation. So a proposed answer to a question, we've used this word a lot today. So this is hypothesis. And a better definition for hypothesis is an idea that can be tested. And there are good hypotheses, that's a plural, and not so good hypotheses. But do you remember from the little pre-lesson what's a good hypothesis? It has to be able to be tested, and it has to either be, you can repeat it, and it's either supported, meaning you were right, you guessed right, or it's not supported, which means it's rejected, which means you were wrong. And it means that if you repeat the experiment, you get the same result every time. That is a good hypothesis, that you can do those things and get your answer. So your scientific method is this organized plan for gathering and communicating, and it can look kind of like this, but there is no one way to do it. You can be in the middle of an experiment and find that there are better ways. We go from point A to point B every time, and that's our scientific method. It's more about managing your variables and communicating accurately and thinking like a scientist than it is about following an exact series of steps. So this is one to kind of keep in your brain too. All right, so who came up with scientific method? This is old business. So we had Aristotle. So we're talking 400 years, 300 years BC. That's a long time ago. And he came up with some of these original ideas. And he talked a lot about how you learn things and then how you apply that learning to to the environment around you. We also had this guy whose name is Ibn al-Haytham. I don't say his name very well, but he also talked about scientific method, and he had stages, kind of like we were talking about before, but his stages were a little more structured than the way we do it today. And then we also had this dude who's very British. This is Sir Francis Bacon. Doesn't he look stuffy? I don't want to hang out with him because he just looks really judgy. I don't know. Does he look judgy to you? He looks like he's looking down his nose at looking right at me like, So, right. Anyway, he was a great scientist, actually. So he talked about how to test hypotheses. And so that's super important. And then we had this guy, you probably heard of him, Galileo. You heard of Galileo? So Galileo is, we call him the father of modern astronomy and the father of modern physics. And Galileo made a very, very important discovery, and then he backed it up with his data, which is what you do. You don't just claim something, you back it up with your data. And he's the guy who pretty much, like, there were guys before him that had this idea, but he's the guy who pretty much said, okay, the earth is not the center of the sun doesn't go around us. Everything else goes around the sun. And in doing that, he was socially ostracized, like he really truly was. He was kind of looked down upon because he was saying things people didn't want to believe, but he had data to back it up. So onto our variables, we talk about variables. So variables are the things in your experiment. So we have something that we call what I change. This was in your lesson. So what you change is what we call your independent or manipulated variable. So in our hypothetical situation with Cal, the different color of the car, the air conditioning, these are all, that's your independent variable. That's what you're changing each time, right? Your dependent variables are what you keep the same, all right? And then having a controlled experiment, this is what, your dependent variables are what you observe, and your control variable is what you keep the same. So your dependent variable is going to change based upon what you changed. So in your experiment, your independent variable or your manipulated variable, well, I like to call them independent variables. We've got this new term for them, I think is goofy, but your independent variable was changing the color of the car, right? In that example. All right. Your controlled variable would be if everything else was the same. You're still in a car, you're going down the road, same time of day, whatever, those things. That's what you're keeping the same. You're not changing stuff. And your dependent variable is whether or not you throw up. If you puke, that's because of what you changed or what you didn't change, right? Your dependent variable is going to change.
Once puked apple juice or orange juice.
I've probably done all of it. I feel you. So if I hypothesize that girls are smarter than boys, and I give a pop quiz on lesson 1, and most of the girls score higher than most of the boys, I could say, therefore, my hypothesis is supported. Girls are smarter than boys. Is that right?
No.
No. Why? There's too many variables, right? Maybe some of the boys were sick. Maybe the girls studied together. There's lots of things that could have changed. You can't just throw out something like that and say, ta-da. Also, when you're thinking about variables, when you do a big experiment, like you'll read things like with the COVID stuff, it's better to wear a mask. You can't do that if you have 5 people in your experiment and you send them out into the world, 3 of them masked and 2 of them unmasked. That's not what you call big sample size. You need to do it with 500 people because that is a bigger sample size, because then your changes are smaller. And it's like if you look at town population, if you have a town with 100,000 people in it, and you have to average out the age of between your babies and your elderly people, and you probably would come to something mid-40s because that's kind of an average. But if you have a small town in which you've got 400 people living, and the lady down the street has had triplets, and her neighbor did too. Now your average age is going to be way low, right? Because those tiny little babies are going to throw everything because your sample size isn't big enough. So that's ridiculous. Ridiculous. You know that's ridiculous. You can't say girls are smarter than boys just like that. But this is something you want to engrave on your brain. So data and conclusions, how does this work? So if your data doesn't support your hypothesis, you get to revise or rewrite, conduct new experiments. That's the way it goes. So developing a theory. Okay, theory and law, this is how this works. Scientific law and scientific theory. We define them like this. A scientific law tells what happens. A scientific theory explains why it happened. Okay, so gravity is one of these things that's a theory and a law. So that one is not a great example to use. But I don't know. There'll probably be an example later on when we talk about this more, and I'm watching our time, but why and what? So why and what? That's what you need to remember. So in this, a good example, if you could use gravity, you would say it, okay, there's a law with gravity. If I hold a ball in my hand and let it go, every time, what's it going to do? Every time it's going to go to the floor, every time. That's a law. If I let it go, it's going to happen every time. Why did it happen? Okay, why? But why? What is that? You have to define gravity. It's a small object being attracted to a larger object. In this case, not the floor, the earth. This small object is trying to get to the larger object, which happens in space. And you'll see that when we get to space science later on. So models. we need models because when we're talking about stuff like, especially in this class, when we're talking about planets and the universe and space and whatever, it's a lot of stuff and it's really hard to conceptualize it or picture it. So models are important. Chemistry too, when you're talking about tiny things like atoms, that's really hard to do. You can't, it's really hard to visualize an atom. We can't even really draw it right. Like the old Bohr model was really good for understanding kind of the arrangement, but they don't go around in circles like planets do. It's the electrons, it's more like a big cloud. So graphs and charts, we use lots of graphs and charts. And it's important to remember when you're doing a graph or like a graph, you've got an x-axis and a y-axis, and we'll do that in a couple labs. So you'll see it when we get there. But this is just ways to communicate science. All right, so let's look at these real quick because I'm watching our time. So scientists use measuring units called what? What do we call them? Do you know? SI units. So that comes from the French, which is Système International d'Unité. And so we have in here, we measure length in meters, mass in kilograms, the effect of gravity, in grams, and the effect of gravity, we also measure in grams. So this is weight. The effect of gravity is weight. So mass is how much matter you're made of, Cal, but weight is how gravity affects that matter. Here's your best example. If you went up in the space shuttle, remember the space shuttle? Or if you went to the moon, okay? You would still have the same mass. You're made up of the same stuff. You didn't lose stuff. But the effect of gravity on you is much less because you'd be kind of floating around, right? Seen the videos of the guys bouncing on the surface of the moon? So that's what weight is. Area is two-dimensional, like surface of the floor. How many tiles do I need? Volume is three-dimensional. We use meters cubed. Meters squared is what we use for area. Density is how much mass is in a contained space. And then time is seconds and temperature. We use Celsius, not Fahrenheit. That's tricky because we use Fahrenheit as Americans, but the rest of the world pretty much uses all of this metric system. Metric system is exceedingly easier because there's no like 12 inches to a foot where there's random numbers. Like the king said, this is how long my foot is. And they're like, oh, this is a foot. It's not like that. Metric system is really easy. So it works like this. You get deci and deca, centi and hecto and milli and kilo. And they go on, and there are others. Oh, they did it the other way? So they did bigger over here and then to smaller?
Yeah.
Well, we'll do a lot of this year, so you'll get used to it as we work. And that's another commit. Now, here's something important to remember. When we do scientific notation, okay, this is how we express values that are really, really big. Like if we're going to give you the distance in meters, a meter is like this long, from the Earth to Jupiter, it's going to be a big number. So sometimes to make that number easier, we narrow it down usually to a number, and sometimes it's a number and then a decimal and a couple other numbers. And then we multiply it by an exponent. If it's smaller, the exponent's negative. If it's bigger, the exponent's not negative. And don't worry, we'll get to this, okay? So don't worry about it. But there's something we do that's very interesting with scientific notation. So if you notice, there's a 3 pattern here. See? After you get past 2, you get 3, 6, 9, 12, 15, 18. Do you see that? Why do you suppose we do that? There's a reason for that. Do you know? So if you write the number, what now?
Exponents?
Yeah, close, but we do that with the exponents. So like if you write the number 4,000 correctly, you write 4, 0, 0, 0. This is why we do it. Because it's much easier to do it in sets of 3 because this is how we write numbers, right? We put a comma every 3. So that makes sense. So let's real quick whip through this because we got about 2 minutes. So you got Earth systems, living systems, physical, cognitive, all this stuff. System is a group of interacting or interrelated elements that act according to a set of rules. And the rules are typically the rules of physics, right? Like I dropped the ball. And we'll talk more about that. This is just kind of getting introduced to this stuff. So according to the laws of thermodynamics, you have 3 types of systems: open systems, closed systems, and isolated systems. And we're going to talk more about these as we go through. But your closed systems, all the energy stays inside, and you can only exchange energy within the system and matter too. Whereas in an open system, you can exchange energy and matter with things outside the system. So we'll talk more about these. And when we do physical science, we'll do a lot with these laws of thermodynamics. They're kind of fun, but open system, closed system, let that bring. So We have open system. Here's your example, pot of boiling water. That water vapor comes out. Now your water is being exchanged with the atmosphere around it, right? And here's another good example of your closed system, a balloon. Okay, whatever's inside the balloon is staying inside the balloon, whatever's outside the balloon is staying outside the balloon. And that assumes that it's impermeable, but if you've ever blown up a balloon and watched it over a course of days, you realize it shrinks. So that latex is not completely impermeable. Some molecules pass out, right? And another example of an isolated system here, so that's gonna be your thermos. You put hot soup in your thermos, it stays hot because it's not exchanging energy with stuff around it. So we call the system of our physical Earth the geosphere. And that's a good one to remember. We call the system of gases surrounding the Earth our atmosphere, right? And that's gonna be one to remember too. We call the system of water on Earth the hydrosphere, okay? These are all ones to remember. And lastly, the living things on Earth are what? The biosphere, okay? And these are all things to kind of keep in your mind, all important stuff. All right, so we're gonna real quick do lab safety, and then we're gonna do a little more when everybody else comes in just a minute. So you probably saw some of these in your binder, right? We talked about lab safety rules. We're gonna talk about that again in just a couple minutes. But things that you guys need to know is, actually, Drew, can you do one thing for me? I forgot. Can you grab my little shelf that contains gloves and bring it down here? I meant to bring that down. So if you ever need certain things,
Wait, bring down the gloves or?
the bin that's got 3 drawers. Thanks. If you need gloves, I'll have them out for you. If you need eye protection or aprons, I'll have them out for you. But there's other things you have to do on your own and know to do on your own. Like when we get hot plates in a couple weeks, you don't stick your hand on the hot plate. Hopefully you know that, right? Like it's called a hot plate because it's obviously hot, right? So how can you get extra points in class participation? So some of you have done this. I think some of you came in late. I did this yesterday morning. So if you've done it since yesterday morning. So if you go and you look at your assignment in your teacher ease, the assignment for watching that pre-video, that there's questions stuck in there. And if you answer the questions, it's going to help you put together a sentence. And that sentence is going to get you 2 extra class participation points. And that'll be extended just until, well, if it's done by the end of today, you'll get 2 points. After today, it'll be 1 point. And then next Wednesday, it's nothing left, no more chances. So if you wanted to check your binder, I have that for you, but I'll definitely throw this up here for a second. And you can always go back and watch the video to see the rest of the answers because you guys have 2 pages, right? So that's what they are. And I may even copy those and send them out with you. But those are going to be your answers. Did you guys get the word oceanographer? Oceanographer, that's what it was. So cool. So I'm going to end our Zoom.
When
Bye.
you're doing the unit 1 lesson 1 stuff.
Yeah.
I was not told that was